In this unit, we are going to be studying chemical bonding. And the first section of this unit is classifying the different chemical compounds. So by the end of this lesson, you should be able to distinguish between ionic and molecular compounds, determine what a compound is based on its properties, and use electronegativity differences to determine the type of bond and identify the more electronegative element. So recall that there are two types of compounds that we have previously studied. You've previously studied ionic compounds and molecular compounds. Ionic compounds are made from, if we look at the composition, cations bonded to anions. So that is positively charged ions bonding with negatively charged ions, and the bonds that they form are ionic bonds. Generally speaking, these are typically metals and nonmetals. However, there are some exceptions. So we generally say cations and anions because, for example, an exception could be when the ammonium ion bonds with the nitrate ion, we get ammonium nitrate, which is in fact ionic. However, if you look at the formula, there are no metals within this formula. However, it's still an ionic compound because it is made up of a cation bonded to a negative anion. So the forces of attraction between the positives and the negatives cause these two to bond. The electrons are typically transferred so that one species becomes positive and one species becomes negative. In chemistry, we refer to a species as, it could be like an ion or it could be a chemical. But for example, ammonium in chemistry is called, it's a species, and nitrate is also a species, right? It's just a way of referring to an entity within chemistry. If we look at molecular compounds are bonded with covalent bonds, and covalent bonds means that they are sharing electrons, and that name covalent directly means the sharing of electrons, because if you are, for example, a co-editor, you are sharing the responsibilities of the editor position. So co-editor, sharing, valent, like the valence electrons, so sharing covalent valence electrons. Most molecular species or most molecular compounds are made up of nonmetals. Okay, so we have now distinguished between an ionic compound and a molecular compound. So that's the first lesson expectation completed. The property of an ionic compound, its state at room temperature, is a solid. At room temperature, it is a crystal. It has a crystalline structure. So ionic compounds have crystalline structures at room temperature. At room temperature, molecular compounds can be solids, they can be liquids, or gases. It just really depends on the molecular compound you're speaking of, because molecular compounds can have a variety of states at room temperature. The melting point for ionic compounds is generally high. And note that I'm saying generally because There might be some ionic compounds that have lower melting points than others, but for the most part they are quite high. The melting point, again, for molecular compounds really depends on the type of molecular compound. So some molecular compounds can have high melting points, and some can have medium melting points, and some can have low melting points. But if we are comparing them to ionic compounds, they are generally lower. Than ionic compounds. Ionic compounds, electrical conductivity as a liquid. So if you took an ionic compound and you raised the temperature to its melting point so that it turns into a molten substance, right? So molten means that it is a liquid. The electrical conductivity is high. So ionic compounds, because they break up into ions when they form a liquid, can conduct electricity. Electrical conductivity as a liquid, though, for molecular compounds is low. So molecular compounds typically do not conduct electricity as liquids. Solubility in water. In general, it's quite high. However, there are some ionic compounds that have low solubility in water. We'll learn about those in the next unit, the unit on chemical reactions. But for the most part, most ionic compounds typically dissolve pretty well in water. With respect to molecular compounds, again, it really does depend on the type of compound. So some have high solubility in water and some have low solubility in water. For example, olive oil is a molecular compound. It's a type of fat. It has very low solubility in water. Whereas alcohol, like the alcohol found in hand sanitizer, has a very high solubility in water. So both are molecular compounds, but one is low solubility in water and one is high solubility in water. So again, it really does depend on the type of compound. Whereas with ionic compounds, in general, ionic compounds are quite soluble. Electrical conductivity when dissolved in water. So when ionic compounds are dissolved in water, the electrical conductivity is high. Whereas when molecular substances are dissolved in water, generally the electrical conductivity is low. Again, there is an exception. For example, in grade 10 you learned about acids. When acids dissolve in water, they actually have high electrical conductivity even though they are molecular. But let's just say here, generally molecular compounds have low electrical conductivity in water because they're not made of ions. They are not charged particles. You can determine whether a compound is ionic or molecular based on its physical properties. So as we can see here, we can take a look at the physical properties and see, okay, well, like looking at the physical properties of a substance, I can guess that it is either ionic or molecular. But as we can see, this can be problematic because there are some exceptions. And so we need a better system to classify whether a compound is ionic or molecular. So a scientist by the name of Linus Pauling came up with the electronegativity scale. And so we look at the difference in electronegativity of the elements, right? And remember that electronegativity is the pull on electrons in element has when bonded to another element. Okay, so this is the way the scale works. Okay, you take the electronegativity of one element and you subtract it from the electronegativity of another element. These lines up and down mean absolute value. And what that means is if you get a negative number, you just make it positive. So, for example, if you were to subtract two numbers, say the electronegativity of this element is 1, and you subtract 2, inside these two upright lines, you would get -1. But when you take the absolute value would just be +1. So what we're going to do here is we're going to take a look at the electronegativity scale. If you do that subtraction, and when you get your positive number, it is between 0 and 0.5, okay, then the bond is what we call just a covalent bond, which means equal sharing of electrons within that bond. So no one element pulls the electrons more than the other. However, if you have a delta En, or a delta electronegativity, between 0.5 and 1.7, that is what we call a polar covalent bond, which means that there is an unequal sharing of electrons in the bond. So this would be like a tug of war, where the rope is the electrons. So you have two people tugging on the electrons. If it's polar covalent, then one person is tugging harder. So the rope is more so on their side than it is on the side of the person that isn't tugging as hard. So that would be considered a polar covalent bond. The electrons are being pulled over to one side. And that's just a general definition. We're going to go into polar covalent bonds a little bit more in greater detail later on in this unit. But I just wanted to set this up as a contrast to covalent bonds, which are equal sharing of electrons. So in this case, there's like a tug of war. However, it's kind of like a stalemate, in which case, no one element is pulling, that much more than the other element. And if we have 1.7 or greater, then generally we have what's called an ionic bond, right? And that's where the electrons have just been transferred. Okay. Again, there are some exceptions. There are some delta ENs that are beyond 1.7 that are still classified as polar covalent, but for the most part, this scale works. So taking a look over here, if delta En is greater or equal to 1.7, so if the electronegativity is greater or equal to 1.7, so it includes 1.7, then it is ionic. This part may have been cut off in your notes based on the 3-hole punching. So it's 0.5, between 0.5 and 1.7, inclusive of 0.5. So if you get 0.5, that is considered a polar bond. So between 0.5 and 1.7, that's a polar covalent bond, which means unequal sharing of electrons. The electrons are pulled to one side of the bond. And if you get between 0 and 0.5, but not inclusive of 0.5, so that means 0 to, for example, 0.4, we would consider that a covalent bond, where there's more or less equal sharing of electrons. If we go over to the next page here, we've got a practice problem. It says determine the delta En for each bond shown and indicate whether the bond is is ionic or covalent. They want ionic or covalent, but I would actually ask you to specify as well if it is in fact polar. So if we look at the O to H bond, we'll just do question A first. So we're going to set this up. Remember that delta En, the difference in electronegativity of one element. So let's do the electronegativity of hydrogen minus the electronegativity of oxygen. And you can find these electronegativity values on the periodic table. So on your periodic table, on the element side, if you look at the legend, you can actually find the electronegativity number. So if we look up the electronegativity number for hydrogen on your periodic table, it should say that it's 2.1. The electronegativity value for oxygen is 3.5. So if we subtracted those two numbers, we would get negative 1.4. But the negative 1.4 is within the absolute value sign, so we change that to a positive, and so we just get 1.4. Looking at our previous page, we can now classify what type of bond this is. Are the electrons more or less evenly shared between the oxygen and the hydrogen here? Are the electrons being pulled to one side? Are they being pulled towards oxygen, or are they being pulled towards hydrogen? Right, that would be a polar covalent bond. Or are the electrons being transferred? Right, is it an ionic bond? And if we scroll up, or we go back to our previous page, we see 1.4 is in the polar covalent bond range. So we would classify this as a polar covalent bond. And if we look at the electronegativity values, we see that oxygen has a stronger electronegativity than hydrogen, which means that electrons in the bond are pulled toward oxygen. Okay, so your homework will be to complete these questions, the answers for which are over here. I do want you to distinguish whether the bond is covalent or polar covalent. That's in addition to the question. And I also want you to look at this question as well. Identify which bonds are more polar. Is this a more polar bond, or is that a more polar bond? And then circle which atom will be more electronegative if the bond is polar. So I want you to do the delta En calculation for this one and the delta En calculation for this one, and you tell me which one has the greater difference in electronegativity. So which of these bonds will there be more of a pull of the electrons to one end of the bond? Then finally, this is also for homework right here. This is a thought lab. So you're given several properties of substances, the melting points, the conductivity as a liquid or when dissolved in water, if it dissolves in water, and I want you to determine, using these right here, put them in the various boxes, right? So for example, let's take a look at sample 2. Sample 2, does it dissolve in water? Yes. It has low conductivity. Okay, so it dissolves in water but has low conductivity. Its melting point is 0 degrees Celsius, so it melts at 0. It is a clear, colorless liquid. We look all along the top here, and we look for a suitable candidate. Well, that's water. So we would write water here, and water is made up of hydrogen and oxygen, which are sharing electrons. So water is a covalent species, right, or a covalent compound. Okay, so complete that for homework along with this question right here and the question above this right here. And let's quickly go back to learning expectations that we had at the beginning of this lesson here. We talked about the difference between ionic and molecular compounds right here. We looked at their differences in properties, and then we used the electronegativity scale to determine the type of bond. Thanks very much for watching.